Happy Friday. Welcome to Friday. And happy third day of this course. This is going to be a review lecture. So if you feel comfortable with everything you've ever learned in your entire life, feel free to zone out and go to a happy place. So last time what we covered were the difference between analog and digital components. We talked about how analog components are used a lot of times in power management, and digital components are used a lot of times in information transmission. Now there is always going to be some crossover. That's not, you can't neatly put components into two bins. But in general, if you need a power solution, you're looking for a more analog component. If you need an information solution, you typically are looking for an IC. So, custodial staff came and wiped my board, and I don't even want to mark on it now because it is just glorious. This is a thing of beauty. I'm pretty sure they actually had to take a floor buffer and get it up on my wall. Nice. I like the blurring aspect. The lighting in here is terrible, so I think I keep blurring out because I don't know, I'm intimidating the camera. Like, what now? So before we get started talking about more course content, we're going to briefly discuss the design problem that I gave for you for this week. Now, the design problem that I gave you for this week, whoa, it's a lot of blur in, blur out. The design problem that I gave you is intended to kind of just be hey, let's get back into drawing circuits. It's a real simple circuit. You have a number of AA batteries, which are 1.5 volts. You have a switch, and you have an LED. And your goal is to make a 5-volt LED light up when the switch is pressed using AA batteries. So you will notice right away that, man, that whole blurry thing is bothering me a lot. Just gonna zoom out a little bit. Maybe that'll fix it. It'll focus on the scene rather than focus on me, because I can't stand still. The thing about the circuit that I gave you is you can't create 5 volts with 1.5 volt batteries. You can take 1.5 volt batteries, and this is what a lot of devices will do, is here's your negative end, your positive end. They'll take a terminal, and then over here, here's your negative end, here's your positive end. And by doing so, the difference between these two wires is going to be 3 volts. Oop, I guess I wrote that exactly backwards. Okay. And then if you keep doing that, you keep daisy chaining these. Positive, negative. This now becomes 6 volts. Okay. And you put 8 in there if you really want to, and it becomes 12 volts. But that's the idea behind AA batteries. Now you can get 6 volts out of this. You can't get 5. So here, this one's at 6 volts. And also, I mean, if you connect to that plate, you can get 3 volts out of it too. You want to have a variable voltage inputs, or some of your components take different voltage inputs. You can pull off of different sections of a battery. That would cause these batteries to drain faster, but whatever. You can do whatever you want. Here, this would pull out a 6 volt. So if you had 4 AA's in series connected positive to negative terminal, this would create a 6 volt effective battery. Now that's great and all, but we need 5 volts. Trying to plug 6 volts into a 5 volt component is generally not advisable. So what I want you to do is do a little bit of research on how do you power an LED. Okay, I'm not going to give you the solution. I've already given you part of it, but I'm not going to give you the rest of the solution. What does it take to power an LED? How do you control the light output of that LED? How do you control how much voltage is going through that LED? If you can answer those questions, then you should be able to design your circuit well enough. So yes, this is a design problem, but this is also an opportunity to do some research, look up some information, gain some knowledge, learn yourself. So yeah, I'm giving this to you to try to break the ice in this course. We're going to be doing similar circuit projects where I don't tell you how to build them, but I tell you to build something. And you kind of have to look up, find out the information on it, look up the circuit diagrams, and you'll have to build them. So, yep, it's just a preview for this course. All right, so now that we've got design problem out of the way, if you have any other questions, you can always email me with questions. Again, that design problem is due Monday at 11:59 p.m. So basically Monday at the end of the day. Please try to email me before Monday at the end of the day. I would appreciate that. Also, thank you to Shane, who caught the fact that question 4 on your reading assignment this week was, there was 2 question 4s in one section, and one of those questions was, do you? So if you answered a question, do you? You won't get points for it. But I do sometimes want to know, do you? Apparently. So again, thank you to Shane, and thank you to Shane for sending me that email twice because I ignored him the first time. All right. There's one little speck there. What we're going to be talking about today is continuing on our idea of building up a review of digital circuits. So today we're going to be talking about truth tables. Okay, if we're going to look at an AND gate turns on when all of its inputs are true, and boy, I keep fading out. My camera is not happy today. I probably need to clean the lens. Oh, of course, you don't give me my dance moves in blur mode, jerk. With an AND gate, it produces an output of true when all of its inputs are true. So let's say you have a 4 gate AND gate, but you only have 3 inputs. If you have a 4 gate AND gate and only 3 inputs, you're going to have to jump one of your inputs to another wire. That's not going to hurt anything. With any AND gate, NAND gate, NOR gate, OR gate, it's a little different with XOR. But with most of the gates, if you have fewer inputs than you do have inputs to your ICs, usually you can just jump them like this, where one pin is connected to another. Yeah, it's really bad. I'm gonna need to wipe off the lens, I think. or something. Maybe get lighting in here. That would be nice. So here I've got A, B, C, and then here's D. And if we're going to create a truth table for this, we got our ABC and our D. If all of these come in at false, this is going to come in at false. This one comes in at true, it's going to be false. And that's the truth table for this. Because there are 3 inputs, there's going to be 8 rows to the truth table. So that's awesome. Easy peasy. But that's what a truth table is. It's just a graphical way of organizing when a system is on versus when a system is off based on the various inputs that it's receiving. Now, again, like I said, it has 3 inputs, so it has 2 to the 3rd entries in this table. If you were to have 16 inputs, you would have 2 to the 16th inputs into that table, and your table would be friggin' huge. I don't want to do that on the board today, or ever. But if I really hated you, I would make you do a 2 to the 16th truth table. I don't hate you. So this is what a truth table is. Now, let's say instead of being given a component and coming up with a truth table as a result of that, what if we were to be given a truth table and asked to build components out of it? This is more of a design type problem, because here you know what you want your desired outcome to be, you know what you want the relationship between input and output to be, but you're going to have to go and figure out how do you actually physically wire something like that. So here, let's say we got, okay, here's your 0, 1, you know what, I'm going to do this. And then we got... okay, so there's all 8 of them. And then let's say we have something like that. Okay? Now, it's not really all that intuitive. Just looking at this, maybe you'll figure out what the necessary solution to this is. But at the end of the day, the end solution is A naught, B naught, C, which is this row, plus A naught, B, C naught, which is this row, plus A, B naught, C, which is this row, plus A, B, C naught. Okay, and that is the solution to this table. Just writing out the 4 different solutions. Heck, you want to take an AND gate for each one of these, and then put all 4 of them into an OR gate. That works. Now you'll have to use a number of inverters. You'll have to invert both A, B, and C are going to have to be inverted at some point. So you're going to have a number of different input wires coming out, 6 different ones, because you have A and B and C, and it gets a little wild. You can do that, and this would take 1, 2, 3, 4, 5 gates. Okay? As we talked about, well, if you've done your reading assignment yet, you know that you kind of want to minimize the number of gates, because the number of gates that you have is directly proportional to the power consumption and the time to completion of the circuit. If you reduce the number of gates, you're in a better place. So this here is workable. It's a correct answer, but it's a very inefficient answer. A better way of doing that is to look at a Carnot map. In a Carnot map, we take all of these inputs and we arrange them not into a table like this, but we arrange them into basically a matrix. Okay, where we're going to take this word, the word is ABC, and we're going to split it. You can either split it A, B, and C, or you can split it A and B, C. Here, I'm going to split it A and B, C. So over here on this side, we have A and A naught. Up here, we have BC naught, BC naught, BC, and B naught C. Now, this is arranged in this way because it follows gray code patterns. Between these four, every time you jump one, there's only one value that changes. So if I jump from this square to this square, B changes from naught to positive. If I change from this one to this one, A changes from naught to positive. If I change from this one to this one, C changes from naught to positive, and so forth and so forth. Okay? You only have one change occurring between adjacent squares in a Carnot map. So if I take all of this data and I say, okay, here we got A naught, B naught, C. So A naught, B naught, C, this is a 1. We've got A naught, B, C naught, A naught, B, C naught, A, B naught, C, which is this one, and A, B, C naught. Okay, which is that one. And everyone else is 0. Now, according to Carnot rules, you can connect values that are next to each other, which that is convenient because it's always nice when you can connect values like this. What this ends up equaling is A, because the common value here is that it doesn't matter what A is. So here it's B C naught plus B naught C. Okay, that's what these two rows represent. You remove the A value because, again, this circle here exists over both A naught and A. So at that point, what that's saying is whatever the gate is that connects those two doesn't really care about which one that is. And over here, similarly, it connects both of these two. It doesn't care whether it's A naught or A. It's going to be true if B naught is true and C is true. Okay, so it's just picking out squares out of this for your Carnot map. And we end up with this result. Okay, this result here is this is an AND gate, and then an OR gate to connect them. This solution here is 3 gates. Okay, and something that is a little bit more obviously visible out of this solution is that we have B C naught and B naught C. Okay, we do have one gate that's in our arsenal that actually does encompass that solution. It's an XOR gate. In an XOR gate, it is true if and only when one is true and the other is false. So we could replace this system with a single XOR gate. And then your solution to, excuse me, your solution to this problem is XOR B and C. So you would take B and C into an XOR gate, and then your solution now is one gate. So yes, you can do it this way. This is valid, but we can reduce this all the way down to one gate. And most of the time you won't be able to do that. Most of the time you'll end up with something where there's like 3 gates, 5 gates. But the reason why you do Carnot maps is that it gives you a whole lot more. It is kind of a don't care condition. Yes, Kenny, because it doesn't care what the value of A is. in fact, you could completely remove A, and it doesn't even care about it. So here, a better way of writing it actually would be this right here, because it doesn't matter. It doesn't care what A is. The only variables that affect the output are B and C. So that's a good catch. Great way to engage the reading material. So that's Carnot maps. I know I didn't cover this nearly as thoroughly as we did last year when we talked about Carnot maps. So if you want, I can give you another example of a Carnot map. This isn't something we're going to be using a lot this class, but in fact, I don't know if we're ever going to use this again in this class, other than maybe next week in your design problem. Did I just say that? Oh, I did. The beauty of this system here, and binary logic in general, is that when you have few inputs and you have few outputs, they tend to be really simple. But as we're going to be working on in this course, which is basically to ensure that we can design very simple computerized systems, this kind of fades away. This becomes nearly irrelevant. So yes, this is the foundational structure of how a computer works, but at the end of the day, these gates are very very primitive, and much lower level cognition than what's going to be required for you at this class. So in recap, digital circuits is all about information. Every one of these components represents a voltage level, okay? 5 volts, 3.3 volts. It depends on what the gate voltage level is for the component. When you're using components, it's important to make sure that all of your digital components run off of the same voltage level, because if they don't, they're not going to be able to communicate with each other. Or it's going to require a converter between every single connection in order for them to communicate with each other. So digital circuits can be a little fickle. Typically, a lot of microcontroller circuits run off of a 5-volt power circuit, and all of the components that integrate with a microcontroller circuit tend to be 5 volts. Now this is nice because Raspberry Pis, as you know, also run off of a 5-volt power supply, and there are a lot of other microcontrollers that run off of 5 volts. Arduinos do. The processors that are used to construct both an Arduino and a Raspberry Pi obviously have 5-volt inputs, but it builds out from there to the point where it's very industry standard to have 5-volt microprocessors. There are also 12-volt microprocessors. Those do exist too, and they exist in 12-volt systems where all of your integrated chips in those systems are 12 volts. A lot of programmable logic circuits, PLCs, do run off of sometimes 12 or even 24-volt circuits, just depending on how well they integrate with the systems that they're supposed to. Like a Siemens system, maybe a 12-volt system or a 24-volt system. It really depends on what the application is and whoever is designing it, how it's designed. There's some benefits to having higher voltage. There's some benefits to having higher current. But that's the basics of digital circuits. If you have any questions, please let me know. I'm going to keep rambling for a few minutes as we talk about what we're going to be communicating next week. I have already given you your project assignment for the semester. You are going to be working on the design of an IoT device. Right now you should be working on some preliminary research for that device by understanding what is IoT. Next week, your project assignment that's going to be due the Monday after this coming Monday is to discuss what are the requirements for an IoT device. All IoT devices have to have a common set of traits, and there is a reason for it. I'm not going to tell that to you now, but we can discuss this once you've handed in that part of the project. But IoT devices themselves all fall into a very strict category of electronics. And one of the beauties of being able to work on IoT devices in this course is that the principles of design for an IoT device turns out that is good practice design for most electronic circuits. So it's something where IoT gives the ability to kind of look into, here is a good set of principles to design your circuits by. Now, not all circuits are going to be built like IoT sensors. In fact, there are many ones that are not. But understanding what the requirements of an IoT system are definitely going to give you a lot more insight and a lot more foundation into how better to build any digital circuit. Because it's a whole heck of a lot easier to undo the strict design considerations for an IoT device to improve its performance in other systems. That is not hard. But designing for IoT itself is actually pretty challenging. And if you took 350 with me last semester, I had you design a light box system, and I think it was Sky who asked me, couldn't we do this better with an Arduino? And I said yes. Because the truth of the answer is that my job in that class, I was not trying to help you design the best light box or the simplest one. I was trying to help you work on some Python coding, integrate a lot of the stuff we learned throughout class and throughout your years here, do a little bit of soldering or a lot of bit of soldering depending on how many times your system fell apart, and do a lot of problem solving. And that worked. In future years, I will probably make that project a lot simpler than what you had to face, but I'm also not going to make it probably nearly as exciting. But the goal there was not best. The goal here is if you design a good IoT sensor, you will have designed it in the best digital electronics design format possible. And that is something that's admirable. So I'm not giving you this product like, I have a gotcha at the end of the semester. Gotcha! I actually convinced you to do it a harder way so that you'd learn. And now you know how to make it better and how you would do it easier the second time. No, this isn't a gotcha system. This is legitimate good design. So next week we're going to be talking about simple design procedures for any electronic circuit. We'll talk about some of the different design considerations, and then I will give you a design problem on Wednesday. I'm probably going to make this design problem just be another drawing, and my reasoning for that is because I am still a little hesitant to be like, hey, heck yeah, let's just jump on ground, start building stuff right away, when, quite frankly, we still don't know whether or not we're going to be facing any quarantine issues. So next week will be a drawing. It will be individual. It will not be group. And I will... I guess I'll see you then. Good luck on your homework this weekend. Send me an email if you need help, or if you just want to compliment me on it, how great my fuzzed out abilities looked when I was totally like blurred. You could always still send me that. Okay. Have a good weekend, and I'll see you all Monday.